Our next speaker is Andrew Tawfeek from Amarist College. He's going to tell us about discrete gradient vector fields and Laplacian of simplicial complexes. So, please, Andrew.
Thank you. I'm Andrew Tawfeek. This was my senior thesis at Amherst College, which got turned in just this December, essentially, and I will be starting my PhD over at the University of Washington in September. I'll be talking about gradients and Laplacians on simplicial complexes. So to start off, let's just define what a simplicial complex is, so we're all more or less on the same page. So this structure up here, we're going to call this K, and it's an instance of simplicial complex. You can really just think of them as generalizations of graphs, where instead of having just 0 cells, which are vertices, 1 cells, which are edges, you're allowed to have 2 cells, 3 cells, etc. In particular, we're going to need the formal definition of this. So formally, a simplicial complex is a collection of subsets of the set 1, 2, all the way up to n. So in this case, n is equal to 5. And what I mean by closure under subsets is, for instance, if 1, 2, 3 is inside K, and that 1, 2, 3 would correspond to this facet here, then all its subsets, for instance, 2, 3, would also be inside K, and that would correspond to this edge here. The elements of K are usually called cells or simplices, and associated to every cell, we have a dimension, and it's just 1 less than its cardinality. So for example, 2, 3, that set has cardinality of 2, but we interpret that to be a 1 cell. And lastly, when you have an element of K, so a set, every proper subset of it is said to be a face of that set. So 2, 3 is a face of the cell 1, 2, 3, and so on. Now, we're going to shift over to the realm of discrete Morse theory, which is where all this will be primarily occurring. So the gradients we're going to look at come from discrete Morse functions, and discrete Morse functions are an assignment of real numbers to every single one of the simplices of your simplicial complex. In particular, you want these two conditions, which are, let's look at first. Don't worry about trying to understand them immediately. You want these two conditions satisfied for every single cell of your complex. So it says for every p cell sigma, so let's just pick a sigma. Let's just say that edge labeled 20 is our sigma. And the first condition says every higher dimensional neighbor of sigma, at most one of them can have a value that is less than or equal to sigma. Well, sigma only has, in our case, one higher dimensional neighbor. It's this two cell that has a value of 18. Now 18 is less than or equal to 20. So this first set has cardinality 1, and that's completely fine because it doesn't go over 1. So this first condition is satisfied. The second condition says the lower dimensional neighbors of sigma, at most one of them can have a value that is higher than or equal to sigma. In this case, these are the two lower dimensional neighbors. Both of them are less than 20, which is fine. The first set just has cardinality 0. And we'd go through and we check these conditions at every single cell. And if it was satisfied, this would be a discrete Morse function on your simplicial complex. And discrete Morse functions are the main thing people concern themselves with in discrete Morse theory. Now, notice how, in this case, the second set had cardinality 0, and the first set had cardinality 1. There are cases where both of these sets are 0, and these cells are very special. They're called the critical cells of your simplicial complex, of your discrete Morse function. And they actually tell you a lot about the topology of the simplicial complex. So they give you information, as we'll soon see, about the Betty numbers and so on, just deep topological properties. But anyhow, so now let's try and shift to gradients of discrete Morse functions, which is what we're mostly going to be looking at, so we won't have to worry about staring at numbers for so long. So given a discrete Morse function, it induces a gradient. So you get the gradient in the following way. You point an arrow from a cell sigma to a neighboring cell of higher dimension tau, if and only if it's pointing to something that is less than or equal than it. So if we looked at this vertex here, labeled numbered 15, its immediate higher dimensional neighbors are these 3 cells here. And we point an arrow to one of them if its value is less than or equal to 15. And you can see, that only happens at the 13. So we'd get an arrow like this and interpret that as the vertex is pointing to that edge. And then we'd go around and do this everywhere. So for example, this edge would point to this 2 cell because 18 is less than 20, and so on. So we can just go around, and you might notice that some of these edges can't actually get a arrow on them because, for example, 18 is bigger than both 15 and 17. And if you remember the previous slide, you'll notice there's something special about the edges that didn't get a arrow, and they're precisely the critical edges. And in fact, the critical vertex is the sink in this case. And that's always going to be the case. So yeah, gradients preserve the critical cells of discrete Morse functions, and they form an equivalence class on discrete Morse functions. And yeah, so what is it? Moving on, I'll tell you why critical cells are important, and then I'll tell you what kind of the main goal of things was. So the reason critical cells are particularly important is if we first label the number of critical cells we have in every dimension. So for example, in this instance down here, the number of critical cells in dimension 0 is 2, number of critical edges is 4, and we have no critical 2 cells. That's always going to be greater than or equal to the ith Betti number, which you can interpret that to be that number of I-dimensional holes. So the 0th Betti number of a simplicial complex is the number of connected components. In this case, it's 1. The first Betti number is the number of cycles. Think like cycles you see in a graph. So this, in this case, would be 3. And the second Betti number is the number of kind of cavities, like think of spheres or tori. And in this case, this has no cavities, so it's 0. And the second statement says the alternating sum of both sides is always equal. But yeah, these are the weak Morse inequalities. They have their complete analogous formulation in Morse theory. And discrete Morse theory is really regarded as kind of mirroring that the smooth case in all situations. So yeah, now hopefully you see why critical cells kind of tell you about the topological structure, and we can kind of get into the main question we wanted to pursue. So going into this, the goal was to understand the number of different discrete gradients that could be placed on a simplicial complex. Clearly this number is finite, and the question is, how does that relate to the structure of the simplicial complex? What we ended up ultimately finding was a connection to what's known as the Laplacian. And you'll still, if you're familiar with the graph Laplacian, you'll see how this generalizes that notion. So associated to a complex, we also have this algebraic structure called its chain complex. And it's a series of maps between groups generated by the n cells. And these maps are called the boundary maps. So for instance, here's our complex from before, and I've highlighted a subset of the 2 cells in purple. If we put these 2 cells into the second boundary map, which deals with 2-dimensional things, so we'd put in only this part, it would spit out precisely its boundary, which would be a collection of 1-dimensional things. So in this case, you can see it would be just kind of 2 cycles stuck together at 2 vertices. And we can kind of interpret this as being a linear map. And because we can interpret it as being a linear map, we can think of it as a matrix. So it makes sense to say, take the matrix, multiply it by its transpose. And that is what the Laplacian is in higher dimensions. In the 1-dimensional case, so when we're thinking mostly about graphs, the first boundary map is usually sometimes called the incidence matrix of a graph. And this is usually called the graph Laplacian in that case. So this really is, in a sense, a generalization of what we see in the graph theoretical case. So how did we get a connection to gradients with this thing, which seems at the moment completely different? Well, it starts with this observation. So I'll move through the 1-dimensional case, and then I'll explain the higher dimensional case. In the 1-dimensional case, if you look at it long enough, you can convince yourself that discrete gradient vector fields on graphs is actually the same thing as just having a rooted forest on a graph. So recall that one of the conditions from earlier said that C1 is always greater than or equal to the first Betti number. So whenever you have a gradient on a graph that has a bunch of cycles, zoom in on one single cycle. That should be a gradient on that one little subgraph. And because of this condition, you know that on the boundary of that cycle, you necessarily have at least one critical edge. Therefore, if you zoomed out and you deleted all the critical edges, you should be left with something that has no cycles anywhere. Therefore, it's a forest. And the second condition, the alternating sum condition, forces things like trees that have no critical edges to necessarily have only one critical vertex, and that all the arrows point towards that critical vertex. And that's how we get this correspondence between rooted forests of your graph and gradients. So we can state this lemma a bit more precisely. If we use m sub k of gamma to denote the gradients having k many critical edges, so over on the left here, this would be an element of m7 of gamma, then we can redefine, we can rephrase this lemma, although it looks a bit silly, why even bother doing this, to say m sub k of the graph is isomorphic to the rooted forest having e minus k. Basically says if you delete 5 edges, you're going to be left with something that has 5 edges less. It's not a deep step that we just took. But it's going to be a helpful step, specifically to use this theorem from algebraic graph theory. So it was proven a long time ago that the characteristic polynomial of the graph Laplacian has this interesting formulation. The coefficients of the graph Laplacian are just the number of vertices in all forests having I many edges. So we can just change the second statement to make it look a bit more clear. It's the number of rooted forests having I many edges. But this is exactly what the sets before were in bijection with. So this immediately gives us that the coefficients of the graph Laplacian are actually these sets of gradients we were just talking about. And if you just plug in one for lambda, you get, of course, the number of all gradients. So instead of leaving these formulas up, here is an example. So this is a cycle graph, which is the little box. This is its graph Laplacian. You'll just have to trust me, and you'll also have to trust me that that's the characteristic polynomial of that matrix. And as you can see, these are all the possible gradients you can have on the cycle graph. And they're in perfect bijection with the coefficients of the graph Laplacian. So yeah, we have, of course it goes backwards, but 16, 28, and 1. So yeah, hopefully I've convinced you that this sort of somewhat makes sense in 1 dimensions. Now, what do we do in higher dimensions? So I'll try to motivate the result I'm gonna propose to you. So recall that the Dth Laplacian now in higher dimensions is the Dth boundary map and its transpose. But here's the thing, the Dth boundary map only knows information about what goes on in D dimensions. It doesn't know what goes on in lower dimensions. So it shouldn't, like, if we found a connection to the characteristic polynomial, it shouldn't be able to tell us anything about lower dimensions. That just wouldn't make sense. So why not redefine this set or generalize the set from earlier to now be the set of gradients on K where interesting things are happening in D dimensions, but everything less than that, essentially everything is critical. There is no interesting gradients or anything going on in lower dimensions. So this really is a set that only cares about the highest dimensions. And then since we have this essentially immediate generalization of the set we had before, why not just conjecture the characteristic polynomial is the same exact thing? The characteristic polynomial of the Dth Laplacian has the same exact statement as before. So we went ahead and tested this in Sage, and we tested it for hundreds and hundreds of complexes, and it worked. Yeah, no, it worked. It went great. Except, of course, we then ran into some complexes that didn't abide by this, like the projective plane, the Mobius strip, and the Klein bottle. And of course, some people will notice patterns between the complexes I just listed. But yeah, well, why didn't this work? And the way we found this out is by trying to prove it anyway. So we tried to proceed as we did before and find a connection between gradients in higher dimensions and a notion of a higher dimensional rooted forest. But of course, the problem is there's not always going to be a one-to-one correspondence. This is especially problematic with things that are non-orientable. And here are an example of some cases. I'll have to fast forward a bit, but essentially what we ended up proving was if your simplicial complex is the triangulation of an orientable D-manifold, this does hold absolutely. If it's triangulation of a non-orientable D-manifold, it does not hold, period. But that's not every complex. Not every simplicial complex falls into these categories. And we have evidence that complexes that aren't orientable, triangulations of orientable manifolds that do work, and triangulations of things that aren't triangulations of non-orientable D-manifolds that don't work. So essentially there's a lot more that can be said that we don't know. And yeah, so that's the big remaining question. So I'll end there. And yeah, sorry for being a minute over.
Thanks so much for this nice talk, Andrew. Let's just thank our speaker for his talk. And if anyone have any question, please unmute yourself and ask it directly or write it in the chat.
So oh, sorry.
Go ahead, Will, sorry.
Oh, so when you're thinking about, so like you have this example of this particular nice identity, this property about particular triangulations of manifolds, which is sensitive to this topological property of orientability versus not. Have you run into any cases where like this discrete Morse theory on these simplicial complexes is sensitive to more detailed topological properties than just orientability?
Oh, that's a very, very good question. That's a very, very good question that I haven't looked into, is what I'm trying to say. I'm curious. I'm sure there is stuff. Yeah, that's something, that's actually a fascinating area that I never looked at. But it does, I would be 200% convinced that other topological properties play a role with these. I mean, clearly, so we did investigate this question quite a bit. Like I personally wasn't satisfied with this statement, and I wanted okay, I want the whole set of complexes. And you do run into having to consider other topological properties besides orientability when investigating this bigger question. Because for instance, yeah, this thing is something that fails. And this is I didn't define what a higher dimensional rooted forest is, but this is an instance of a rooted forest of the equilateral bipyramid that fails, whereas other two-dimensional complexes work. So there's some topological property concerning this thing that at least I couldn't characterize. Yeah, that's making it fail. So there are other topological properties coming into play here that at least I personally don't understand. I would encourage you, if you're interested, go for it. But yeah, no, there definitely seems to be a lot more that could be said that I just didn't know how to find.
I guess at some point you run into continuous Morse theory, and maybe that's where this connects up. I don't know about that.
Yeah, there's definitely a connect. You can start thinking about connections what is it? Just because triangulation manifolds come up, you can start looking at manifolds in general and their PL triangulations and all that stuff and so on.
I have a question. Well, more than a question, is just a comment. This reminds me a lot of the critical group of simplician complexes. The critical group is just the torsion part of the co-kernel of the Laplacian matrix, and that is quite related with the complex exchange that you mentioned before. And there is one extension to these critical groups, to the simplician complexes, and one study was done by Carl Clevans, Kieran Martin, and another person, and possibly this can be connected to the work of them. So it's just that is just the comment that I wanted to mention.
Yeah, actually speaking of Caroline Clevans, I didn't mention it. I mean, you can actually see her work show up here. Yeah, this is the stuff I skipped of what a higher dimensional rooted forest is, and yeah, her work is present all over in this. In that, yeah, her higher dimensional rooted forests are completely her creation, and yeah. But yeah, I'll look more into her work based on your suggestions. But yeah, her work played a big role, and yeah, this theorem on the screen is the generalization of the one we had before, except you might notice there's this horrible weight that now shows up, and basically accounts for torsion. Because things get messy when you're thinking about dimensions bigger than 2. Like for instance, if d is equal to 1, like in our case, this thing is always just going to be 1. But yeah.
Could you possibly go back to the part where you talk about how all the interesting information in your complex was at the dth level?
Oh, sure. Like the stuff?
Yeah, because this reminded me of a assumption that comes up in the high dimensional expander literature, where they essentially assume this exact same thing, that the only interesting part of the complex is at the dth level, and then every single possible excuse me, every single possible simplex in levels d-1 and below appear, essentially, so that the complex restricted to d-1 and below has trivial homology. I was wondering if there was any connection that you had here, given that a lot of the high dimensional expander stuff is looking essentially at eigenvalues of these Laplacians, that sort of thing, and these sorts of up-down walks that you were talking about with the discrete Morse functions anyway.
I've never heard of high dimensional expander, anything. Like, this is my first time hearing those words all put together right next to each other. But yeah, no, that's fascinating. Yeah, no, that seems incredibly interesting, and that's a connection that I don't know a single thing about, admittingly, but it sounds super, super fascinating.
Yeah, no problem.
Yeah.
Well, I just don't like to interrupt, but if you guys have any other further questions for Andrew, maybe you could just contact with him directly. I think we need to finish this session, and please let's thank our talker again. Like Andrew, thanks so much.